Alright guys, the last thing we're going to do in terms of talking about phase change is discuss phase change diagrams. I believe Akins and I actually talked to you guys about these last year, or at least showed them to you. So hopefully they're not too new looking, but just in case we didn't discuss that last year, let me just kind of show you what this is showing. So when we talked about the heat curves, which were the little stair-step things we did earlier, that is only looking at phase changes at 1 ATM, so our normal boiling point and our normal freezing point and that type of stuff. However, if we are to really understand phases and phase changes, we have to recognize that pressure plays a huge role in terms of the temperature in which something freezes and boils. So for example, we're in the midst of January, February range where we get all our snow days. So let's say it's raining outside and it's 32 degrees Celsius, or Fahrenheit, excuse me, and we're thinking, oh, we're not going to have school because it's going to freeze, but all we get all day is rain. Why are we only getting rain or water when the temperature is low enough and at the freezing point? Well, the reason being is the pressure is not where it needs to be for normal freezing point. In other words, at 32 degrees Celsius, or Fahrenheit, I'm sorry, I keep saying Celsius. At 32 degrees Fahrenheit, in this particular circumstance, the pressure is not going to allow it to freeze, so all we're going to get is just a cold rain. Okay, so pressure plays a very, very big role in terms of phase changes, and that's what this is looking at. This is looking at how all the pressures affect the temperature in which something changes phase, and what these black lines are representing are the phase changes. So we always have solid all the way over here to the left. In the middle, we have our liquid, and all the way over to the right, we have our gas. Okay, and each of these black lines actually represents that equilibrium point, that phase change between those phases. So at normal, if we check this out, which is 1 ATM, this point right here is where we go from solid to liquid, and this is H2O, this is water, which it actually says right here. Notice what temperature that is that's 0 degrees Celsius. Still at normal, going all the way over, we hit our next phase change right here. Going from liquid to gas, guess what? That temperature is at 100 degrees Celsius. But let's say we're actually at a lower pressure. Okay? For example, let's say we are up in the mountains. Okay, the pressure at sea level is 1 ATM, but as you move up into the atmosphere, going up into the mountains, our pressure is going to actually decrease. So let's say we're about right here. Okay, we're going to draw kind of as straight a line as I can get, dotted line all the way across. Okay, notice here where our temperature changes, or where our phase changes, is actually a little bit higher than 0 degrees Celsius, or over here it's actually a little bit lower than 100 degrees Celsius. Okay, and that's specifically for water. The pressure will affect different things at with different substances. Pressure will affect it differently because this phase change will look a little bit different. So notice like this phase change diagram over here, I believe this is for carbon dioxide, but I could be mistaken. Notice here where the lines are a little bit differently shaped. And that's because it's a different substance. Also, something fun about phase change diagram, notice this line right here between solid and liquid. It's got a negative slope versus over here it's got more of a positive slope. This is actually an indication that the solid will be less dense than the liquid. Just kind of another fun fact to show at you in terms of phase change diagrams. So what do you need to be able to do with the phase change diagrams? First off, you need to recognize the different phases, recognize that the lines are the phase changes. You also need to recognize two important points. Okay, and let me clear off some of the writing right here. This point right here where the T's next to it is called the triple point, and we can see that over here as well. What's kind of fun about this is notice where all three black lines come together is actually where all three phases exist at the same exact time, meaning all three phases are at equilibrium with each other. Okay, now for water, that's not going to happen naturally. We're never going to have this low of a pressure just naturally occurring. Okay, so that's only going to occur in a lab-based setting, and you can actually look up a video of it. It's pretty neat. It really doesn't show much, but it's kind of cool to look at. Okay, and then the other point you want to look at is the X up here, which you see over here is called the critical point. Okay, and the critical point is important because notice here we've got this really high temperature, but we also have this really high pressure. And what that basically means is this substance is at such a high temperature that it should be a gas, but it's at such a high pressure that it can't be a gas. And we actually call it either a superfluid or a critical fluid. Okay, either way you want to think about it. Okay, and those definitions are down here. I'll scroll down just so you can kind of see them. Not sure what it just did. But let's move that back up there. Okay, so a triple point is where all three states of matter exist, and then the critical point is where the pressure and temperature are so high that we end up with that intermediate fluid is the other way you can call it. Superfluid, critical fluid, intermediate fluid, all kind of used interchangeably, where it's neither a vapor, it's neither a gas, nor a liquid at that point in time. Okay, so some things that are important on here is like what we already discussed is that difference in density between the solid and liquid, and really that's more like a trivia thing. That's not something you need to know for the AP exam or anything like that. But something that you need to know for real life is, let's say we are up in the mountains, and we already kind of discussed that a little bit. This thing moved on me. So let me see if I can realign it a little bit. Okay. Let's say you're up in the mountains and you like to bake or like to cook. What do you know about cooking up in the mountains? Well, you cannot necessarily use the same cook time or even the same cooking temperature as you do down in the lower part of Cherokee County. The reason being is this pressure change right here. So again, notice when you are boiling water up in the mountains, its temperature actually boils at a much lower temperature. Okay, that lower temperature, actually what that's going to affect, first off, because you're cooking something at a lower temperature, that means it may not denature the proteins as well at that temperature, so you may have to cook it longer to denature the proteins. So like if you're cooking an egg up in the mountains, you may have to cook it longer than what you would down here because it's actually cooking at a lower temperature because the water may be only boiling at 95 or 90 degrees Celsius, depending on how high you are up in the mountains. Or let's say you're baking cookies. Okay, well, to get the cookies to bake the way you want them to, you may have to increase the temperature that you're putting the stove to so that they actually cook well enough to cause the baking soda and everything to react the way they're supposed to. So just again, kind of a fun fact to kind of think about as you're going through. Okay, and again, the reason being for that is because remember that the definition for boiling point is when the vapor pressure equals the external pressure. And because the external pressure is lower, vapor pressure is going to hit it much sooner, and therefore it's going to boil at a much lower temperature. Okay, so moving on from that, that is the end of Chapter 10. Moving on to Chapter 11, looking at solutions. Okay, first thing, of course, we have to talk about with solutions is concentration. And you guys are already pretty adept at calculating concentration. Okay, specifically the one we use is molarity. And hopefully we're already comfortable with these terms, but just as a review, a solution, of course, is a homogeneous mixture. It's where you have a solute and a solvent. Remember, solute is the shorter word. It is the smaller amount of stuff. So like salt and salt water. Solvent is the longer word. It's the more stuff or the more present stuff. So that would be like the water and salt water. We have our terms dilute and concentrated. Again, hopefully we know what these terms are. Otherwise, we may have an issue. Dilute being not a lot of solute present. Okay. Concentrated meaning a lot of solute present. So like dilute would be watered down tea, if you will. Concentrated would be very strong tea. So that's kind of what we're looking at in there, like really, really just a little bit of sugar in your tea so it's not very sweet versus good old-fashioned Southern tea where it's basically dripping sugar. Okay, so those are terms we need to make sure we know. Now, how do we express dilute and concentrated? Well, we use either molarity, mass percent, mole fraction, or molality. And really, we're not going to focus a lot on molality. You guys did a little bit of that last year when we did our colligative properties. Colligative properties are no longer really part of the AP exam in terms of calculations. They are in terms of concepts, so because they're not part of calculations, I'm not going to spend a lot of time calculating molality, but we are going to just go over it just briefly and make sure we're good to go and comfortable with it. Okay, just because you are going to see it in college and you are going to need to be able to use it in college, but it won't be on the AP exam. If you actually look at your formula sheet, the molality equation is not on the formula sheet in any way, shape, or form. But just to kind of review, what are our equations? Molarity should be one we are very comfortable with at this point in time, which of course is our moles of the solute over the liters of the solution. And I am making a definitive difference here because molality is a little bit different and therefore our calculations are a little bit different. Okay, mass percent is exactly what it sounds like. Remember, any percent is going to be a part out of a whole. So this would be the mass of either the solute or the solvent. It could be either one. okay, over the mass of the total solution. So you have two different mole fractions, or sorry, not mole fractions, mass percents that can happen here, but a lot of times they are expressed in terms of the solute, but it could also be expressed in terms of the solvent. But a lot of times, like when you're reading the back of your toothpaste bottle and it says it's 9% fluorine by weight, they're referring to the solute versus the total solution. Okay, mole fraction is something you guys have actually already done, okay, believe it or not. It again is the moles of the solute, or again the solvent. It could be either one, though again a lot of times it is a solute, over the total moles of the solution. Okay, and then molality, of course, is our last one. Okay, which is the moles of the solute. So again, almost identical to our molarity equation. And notice this is an italicized M versus a capital M. Okay, but the difference here is instead of liters of solution or even kilograms of solution, it is kilograms of the solvent. Okay, so those are our equations. And again, this guy is not on the formula sheet, okay, nor is technically your mass percent, but be aware it is something that shows up. Any percentage can be on the exam, whether it's on the formula sheet or not. Mole fraction is on the formula sheet. It's under the gas section. Okay, and of course molarity is on there as well. So what I'm going to do is I'm going to stop this video for right now. We're not quite at the 15 minutes, but I want to do some calculations with you guys, and I'm not going to have the time to do that right in this video. So we're going to stop for a minute and then come back with the next one. Thanks.